Yes, now we are live, Professor. We may start.
Okay. 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 So good evening. So this is our third session. So we were discussing some basic principles of quantum mechanics, and we were trying to develop these principles based on some experiments. We are trying to somehow at this point we can say they are thought experiments, but these experiments with the current day technology can be realized in the laboratories. So if you remember last lecture, we said we are interested in understanding what is called wave particle duality. But our discussion in the last two classes appeared that we are actually not discussing this, probably deviating it a little bit. But I will try to see in this class if you can see the connection of what we are discussing here. So let me just recall one or two points that we discussed last time. Suppose if I have a source which is emitting photons, okay, so I'm just writing this as discrete. Then I have a beam splitter, and then I have a detector D1 here and detector D2 here. Okay, so there is a possibility that a photon that comes here can be transmitted or it can be reflected. Now, observation is that the photon, so observation is that either D1 or D2 will click for a given photon. So from this result, what can we conclude? We can conclude that a photon either so for a photon, let me write it like this: for a photon, either T or reflection, either transmission or reflection occurs. And also we observe that we will not be able to predict. So we cannot predict, which implies either T or R occurs randomly. It occurs randomly because we cannot predict this. So this is our conclusion from this observation. Now further, if n photons are used, then on an average n by 2 will reach D1 and n by 2 to D2. Okay, so that means from this observation we can say that probability of transmission is equal to half and probability of reflection is also equal to half. Okay, so we are making an observation and we are concluding something from that. So this is the observation and this is the conclusion, and this is the observation and this is the conclusion. Okay, So now what can we say about this photon? Okay, so photon. So from this we understand that so this is one experiment. Let's say this much is what we have concluded. Then we are going to look at another experiment. Okay, this is also, we discussed this in the last class. Now this experiment is that I have a source, and then I have photons, and then I have a beam splitter. I will call this as beam splitter 1. And then there is another beam splitter here. This is beam splitter 2. And then I put another beam splitter here. This is beam splitter 3. And there is a possibility of, I put a detector D1 here, detector D2 here, and detector D3 here, and detector D4 here. So in this particular experiment, so this is transmitted. This is 2 times transmitted. This is transmitted first and reflected next. This is reflected. This is reflected and reflected. This is reflected and transmitted. Now, what is the observation here? So the observation here is that D1, D2, D3, D4, okay, D1, D2, D3, D4, all will receive n by 4, n by 4, n by 4, n by 4, of course, on an average. This is very important because we will never, any random thing, we can only talk about average behavior. From this, what we conclude? We conclude that probability of TT is same as probability of TR, is same as probability of RT, is same as probability of RR, and that is equal to 1 by 4. And more importantly, this is transmitted does not mean that it will again be transmitted, or this is reflected does not mean that it is again reflected. So the transmission and reflection is not going to change anything of what photon state is in some cells. Okay, so no selection. Okay, so either T or R are not selected by beam splitter. This is the lesson that we have learned from here. Whereas in the polarization experiment that we discussed in previous class, such a selection takes place. Once it is transmitted, it will be transmitted with the polarizer of same axis again. Or once it is absorbed, then anyway it does not come out for that purpose. So that kind of a selection does not happen in this particular case. Okay, so this is what we have learned, and these are the conclusions that we have drawn in the last class. Okay, now let's continue from here.
Sir?
Yeah.
Sir, for a random variable, we could talk about the average, but also the standard deviation, sir. So
Yes,
how can
yes.
we calculate standard deviation here for the fluctuation? Like for if we have had one beam splitter, then we could have like binomial distribution. But we have like 4 outcomes, no? T, T, T,
Yeah.
R, T, R, R. So how can we calculate the variance or standard deviation here?
Yeah, so you can think of a multinomial distribution. So if you have more than 2, so generalization of a binomial distribution is a multinomial distribution.
Okay, sir. Okay.
Yeah. Okay. So
last week you were talking about unitary operator, sir. Like you finally told that this is an unitary operator.
Yes. Yes.
Like, what do you mean by that? Like, what exactly from the result? How can you say that it's an unitary operator?
Yeah. So I will come back to that point today. But let me discuss one more experiment before I come back to that. So what I made, the precise statement that I made is that beam splitter is like a unitary operator. So this is the statement that I made in the last class. So I will amplify on this. Okay, whereas the polarizer is not like a unitary operator. That's what I meant. Okay, so now let me just present one more experiment. So here I am going to actually do something similar, where I have a source, and then I have these photons coming, and then I have a beam splitter here. So I call this as beam splitter 1, and there is a transmitted possibility. But now what I do is that I don't put a beam splitter here, but I simply put a mirror. So this is how we define a mirror. So this is mirror M1. What does this mirror do? It simply reflects this. It actually alters the path of the photon. So let's say this comes like this. Now this reflected one, I will put a mirror here. I'll put a mirror here. So let's call this as M2. And then it gets reflected in this particular direction. Now I put a beam splitter 2 here. Okay, so this is my beam splitter 2. Okay, and I have, so now what I do, I put a detector D1 here, and then put a detector D2 here. Okay, so just like in the beam splitter, we have transmitted and reflected. The mirror will have only reflected. It will not transmit anything. So let's assume that these are perfect mirrors. That means there is no loss. They don't absorb. They simply reflect the full, they reflect the full photon. Okay, so that is what these ideal mirrors do. Okay, so now we have this kind of a scenario. Now, if you look at this first beam splitter, this is transmitted thing. This is a reflected thing. Now, mirror does not have two options. Mirror has only one option. So let's not say anything. So this entire wing is a transmitted thing. Now, this is a beam splitter. So here you can actually have transmission or reflection. So now suppose this transmitted one is transmitted once again. Where will it go? It will come to D2. That means transmitted will come to D2. Now transmitted and reflected will go to D1. Transmitted and reflected will go to D1. Now reflected and transmitted will also go to D1. Reflected and transmitted will also go to D1. Reflected and reflected will go to D2. Is that clear? If the photon, so T and R are corresponding to actions at these two beam splitters. Mirrors, they don't have any such action. Okay, mirror is simply going to alter the path of the photon. So when I say TR,
Sir,
transmitted at, yes.
Sir, can you repeat this, sir?
Yeah. So when I say TR, that means transmitted at, let's say, beam splitter 1, and reflected at beam splitter 2. Okay, so this is the kind of nomenclature I am using. So let's say this, so let me just show you. So this one is transmitted here and comes here and then reflected here. So that is my TR. Follow? Now transmitted and transmitter will come to D2. Reflected here and transmitted here will come to D1. Reflected here and reflected here will come to D2. Is that clear? Is the nomenclature clear? Syed, is that clear?
Yes, sir. But can you change the color of this notation, sir? For that, can you change the color of this transmission and reflection, sir? From where
You
to
want
where?
color?
Yes, sir. It will be more.
Oh, you are asking me to.
Change this color for this transmission and reflection. That will be more visible
Okay,
to see that.
so let's say this is transmission and this is reflection. So this is TR. Okay. And let us say so let's say this is transmission and this is transmission. That is TT. You follow? Now you
sir.
imagine.
Yes, sir.
Now imagine RT and RR. That is
Okay, sir.
okay. Otherwise, this figure will become very clumsy. Okay. So now the question that I am asking and the question that I want you to give me the answer is the following. Okay, so anyway, for a given photon, what happens we don't know. Okay, what happens at this beam splitter also we don't know. What happens at this beam splitter also we don't know. Okay, now the question I'm asking is, if n photons are used, let's say n photons are used. Okay, now on an average, number of photons in D1 and D2. Number of photons at D1 and D2. What will be your answer? How many will come to D1? How many will come to D2?
So 0 to D1, sir.
Okay, so that is one answer. Let us say nothing comes to D1 and
Everything comes to D2.
everything will come to D2. Okay, that is one answer. Okay, so that means what? Nothing comes to D1 and everything comes to, all n will come to D2. So is there any other answer? That is, you may have some logic, right? What
n by 2.
Okay, so that is another answer. So n by 2. Okay, so any other answer?
Sir, at D1 n by 4 and at D2 3n by 4.
Okay, so this is n by 4 here and 3n by 4 here. Okay, any other answers?
So n by 4, n by 4.
What happens to half of the photons? Total number should be n by n. No, we are assuming that no photon is lost.
Sir,
So, but in the first beam splitter also it's splitting to half and half, right?
Correct. But either half of them will come to transmission or reflection. These mirrors are not eating away any photons. So somehow photons should come out, no?
Yes, sir.
Every
So,
photon that started at S should come to either D1 or D2, right?
oh, yes, sir.
So we cannot miss that. The total should be equal to N.
Yes, sir. So n by 4, 3n by 4.
Okay, N by 4, 3, N by 4. Okay, so now we have this. We have this 3 answers at least you have given. Now I want to just get. I don't know how many of you are there in the 20.
26.
26. Okay. So I want to just get a quick statistics of this. So how many of you think that this n by 2 is the possible correct answer? Can you please raise your hand using that raise hand tool? So this vote is for n by 2, n by 2. Candidate is n by 2, n by 2. Okay. So I have seen some 8 of you have raised hand for this. Okay, so now you please lower your hands. Okay, actual who is raising, I'm not actually looking at. Okay, now let us look at this choice, n by 4, 3, n by 4. N by 4, 3, n by 4, 5. Okay, so let's say 5. Okay, so please now about this option, that 0 and n. Okay, four participants have raised. So 17 of you have okay, 5. So let's say 5 participants have raised. So something like 18 of you have raised, and I think some 8 of you have not. So among these 8, do you want to suggest any other option, or do you want to suggest any other option? Okay, so but my humble suggestion and request is that all of you should either say one of this is, I mean, it's not, nobody knows the correct answer at this moment. So you are trying to make an educated guess. Now, of course, to say that your educated guess is correct, that means you should have sufficient education, right? And this exercise is to impart you the education. So if you don't have, it doesn't matter, you can get the education. And especially this is something which we are learning quantum mechanics. Therefore, it is okay if you are not correct, because there are many people, even experts sometimes may not be correct when it comes to it's a subject which gives surprises at all levels. Okay, so now let me invite one of you who have given your raised your hand for this n by 2 among these 8. So one of you please volunteer and say, why do you think n by 2 is the right? Why do you think this is the answer?
Sir, may I, sir?
Yeah, please.
Sir, from beam splitter 1.
What's your name?
Said Ibrahim.
Sorry, tell me.
From beam splitter 1, n by 2 is transmitted and n by 2 is reflected.
Correct.
Then mirror 1, n by 2 transmitted also reflected. Then beam splitter 2, the reflected n by 2 is splitted into n by 4, n by 4. That's why I thought. Then
Correct.
Mirror 2 reflected from beam splitter 2, splitted into n by 4, n by 4. So totally n by 4 plus n by 4. From D1, from D2, n by 4 plus n by 4. That's what I thought.
Okay. So that is your idea. Very good. Okay. From this n by 4, 3n by 4, we have 5. So can someone volunteer and then explain why this n by 4, 3n by 4 is your guess for the answer? As I told you, I haven't noted the names. So if you volunteer, only then I will know that. But there are 5 people. So I hope one of you can. Sharath, you want to say something, or you forgot to lower your hand? Okay, anybody from this 5? Please come forward. I want to know what you are thinking about this. Don't take advantage of my not noting the names. Okay, who has raised the hand for this 5? N by 4, 3, n by 4.
Sir, actually, I made a mistake in beam splitter 2. I did not notice that. First of all, I don't know how mirror will operate. I made a mistake and I thought it will be n by 4, 3, n by 4.
Okay, so now what after?
Now it's coming as n by 2, n by 2. I'm not sure, sir, how a mirror will function. I don't know. Like polarization is like a measurement, and beam splitter will operate as a unitary operator. So how does a mirror function?
Okay. So
first I considered that all n by 2 will just get reflected.
Correct.
Then again at beam splitter, both the options are open. So half of them means n by 4 will get transmitted and n by 4 will get reflected. So in that way, it will come as n by 2, I think.
So you are now probably trying to change your option from this to this.
Yes, sir. Okay.
So I think this is going to win with more majority. Okay.
But okay, we'll see.
Okay. So is it that all of you who have opted for this 5? So you think it is all of you are having second thoughts on this, or any of you have some argument to stick to this n by 4, 3, n by 4? Okay, so now let me come to this 0n. So 0n category, I think we have some 5 people who opted for this. Okay, so let me ask someone other than Debanjan. Debanjan, we will come to lastly. Okay, who are the others who opted for 0n? Okay, please come quickly. You should not. Shitikanta.
Yes, sir. I have opted for.
You have opted. So, but let us wait if
Okay,
somebody
sir.
else.
Yes, sir.
Are any of you like Arpita has said, you have thought about this, but now you think it is not. After a very scientific explanation Saeed has given, have you changed your mind? Okay, so let me go to Debanjan. Debanjan, tell me, why do you think 0n is correct?
So
Sir?
interference is taking place.
Sir?
Yes, yeah.
So will mirror change the phase by 180 or something like?
No, at this moment, let us say that, see, we are only asking this question about the number, no?
Okay, sir.
Okay, so mirror is going to send all of them, just change the path, that's all.
Okay.
Sir,
Yes.
even if the mirror is not there also, the result would have been same, right? Mirror means
See,
I have
mirror-
some arrangement which will divert the path. Then also the
Correct.
result.
Correct.
Yes, sir.
I want somehow bring both the beams to this beam splitter, that's all.
Yes, sir. Yes, sir.
You do that with mirror or something else, it doesn't matter.
Okay, sir.
Hello,
so
sir.
Devanjan says some interference is happening.
Yes, sir.
Okay.
Because TT and RR will constructively interfere, and others like TR and RT will destructively interfere.
Okay. So Devanjan has an argument. Okay. We are talking about photons. And how many of you think that this constructive and destructive interference is possible in this? Please raise your hand. Yes, constructive and destructive interference is a possibility. Okay, so okay. Now, please understand this. If I send a photon, let's say a photon is emitted. A photon is emitted from S, and a photon is detected either D1, either in D1 or D2. Till that time, my second photon is not emitted. Okay, one photon is emitted, it is detected, only then the second photon is emitted. Okay. Now, if you say there is an interference, what is interfering with what?
So with itself, sir. The photon is interfering with itself.
Okay. So if a photon is interfering with itself, is photon a wave or a particle?
A particle, sir, but
How
here,
particle will interfere with itself?
but it has duality properties. That's how.
A photon, if it is a particle.
Sir, I'm getting confused at this point, sir.
What is the confusion?
Means how can after indifference, so that the second option will only be correct, because 0 and n cannot be, so means cannot happen, because after one photon is emitted, then the other photon is emitted, then that means it has both the probabilities, right?
Yeah. So you are what are you saying? Interference cannot happen, you are saying, or n by 2 is the right answer you are saying?
Yes, sir. Base means when you made a statement that after one photon is emitted, then only the second photon is emitted, then means it is totally 1 by 2, n by 2, n by 2. It cannot be
Okay.
0 and n, right?
Okay. So are you one of them who said 0n initially? Was your
I don't know. No, sir. I said n by 2, n by 2.
n by 2, n by 2. Okay, so let
But
me say,
sir, like the photon has a equal probability of like transmission reflection from beam splitter 1. So it can interfere with itself.
yeah, but these two things don't seem to they are not seem to be connected, right? There's a equal probability does not mean that it should interfere with itself. A given
Yes, sir.
photon has equal probability,
Yes,
but
sir.
suppose it is transmitted, for sure it is not reflected, right?
Yes, given that it is transmitted, it's not reflected.
So if it is equal probability, does not mean that if it is equal probability and it once it is transmitted, it is not reflected. These two statements are not contradicting each other, right?
Yes, sir. Yes, sir. But like this is Mach-Zehnder interferometer, if I think it correctly. So with single photons, Mach-Zehnder interferometers can be operated.
Yeah. See, whatever is the name, we are trying to understand what is going on here. What is the mechanism by which what is observed is correct? Okay, how to understand what is observed? Okay, so now the question that I'm asking is, you have one photon is emitted from S, it passes through this entire operator and gets detected. Only then the second photon is sent. Now, if you say that all the photons will come to D2 and no photon goes to D1, that means I can predict, right? I am sending a photon, it will go to D1. I am sending a photon, it will go to D1. If all the photons are coming to D1, I can predict, right? Even though there is a randomness at BS1, there is a randomness at BS2, somehow two randomness are going to cancel each other and I am able to predict that the photon will go to D1. A given photon will go to D1. I can predict that. Correct? Is it very surprising? Or do you think it is possible to do that?
Actually, sir, what I think is like there is a confusion between above experiment and this one, sir. Like because of mirror, we are getting different answer. Like if we think from above experiment, if we think, then n by 2 is correct option. That if we don't think M1 and M2 as an any measurement operator.
See,
if
yeah.
we
So
think M1 M2 as an
see, what I'm trying to tell you, trying to tell you is, can you hear me?
Yes, sir. Sir, I have a doubt.
Yeah.
So, is there any rotation from the mirror?
Yeah. So let me clarify what mirror does. See, mirror is not going to change the quantum state at all. A photon is coming, it will, so understand this mirror as simply is changing the path of the photon. No other changes that are given. Now, why I want these mirrors? I want these mirrors because I want them to meet at BS2. Both of these beams, they are meeting at BS2. Otherwise, what happens? This photon will go in the horizontal direction. This photon will go in the vertical direction if I don't have mirrors. So how do I make them meet at another beam splitter? Is by putting this mirror arrangement. Other than directing the path of the photon, this mirror is not going to do anything. It's not going to change anything physically of a photon. It's only going to change its path. Okay. So the difference between this experiment and previous experiment is, if you think it is because of the mirror, it is not because of the mirror. Mirror is not going to do anything to the, it's not like a measurement, it's not a unitary rotation. It's simply changing the path of the photon. That's all. I could have, instead of this mirror, I could have put an optical fiber and then bend this optical fiber in this fashion. That is also okay. so that photon will go through the optical fiber, and I change the path of the optical fiber by simply putting it in this right angle. Then that also will do the job. Okay,
Sir,
so is
now
that clear?
question arises. Yeah, like in previous experiment, then like in first beam splitter, if we split like transmission and reflection, then again when you come back to beam splitter 2, then it will sense that like there is a transmitted beam and reflected beam. That's why you are getting transmitted plus reflected one, like n number of particles.
Yes.
Yeah, if we take above experiment, can you scroll down, sir? Like,
I mean, you are saying that 4 detector experiment, right?
yeah.
This one.
Yes, sir. Here, like, what is the difference? Like, here you have one transmitted beam from BS1. And BS2 should feel only transmitted beam, right? Like whatever, like if we are seeing here.
But that's not the result that we observe here. Here we observe all of them getting n/4, 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 n/4.
Yeah, this is confusing now. Like,
Sir, I have a doubt, sir.
Yeah.
Sir, if we remove the BS2 beam splitter, what happens, sir?
Where
will it produce it from the third one?
Oh, from this experiment. That's a good question. Saeed, who is asking? Saeed, no?
No, Abhijit.
Abhijit, okay. So I think you asked a very good question. So let us say remove BS2. Remove BS2. This is a nice way of thinking. So if you remove BS2, then what will happen to D1 and D2? Okay. So what do you think? Abhijit, what do you think will happen?
Sir, definitely the photon will come. If you place one, if we let go one photon, then photon should come at the detector.
Correct. But now if I have n photons, how many of them will come with D1 and how many of them will come to D2 on an average?
Sir, will that interfere, sir? That's my doubt. Will that interfere, or just if it misses the path, it should be 1/2, 1/2 only? Because
misses the path means
it is. Means if the photons collide, it will produce an interference. Or
no. See, please remember that I am having only one photon at a time. There are no two photons.
Okay, then there are equal probabilities that it can reach D1 or D2. n/2,
so
n/2.
you have to get n/2, n/2. Right?
Yes, sir.
This is correct. So what does that mean? That means that there is no difference between this one and our first experiment. Okay. What was our first experiment? Our first experiment is, you have this experiment, right? One beam splitter, D1 and D2, right? So we said you will get n/2, n/2, right? Same thing will happen here.
Yes, sir.
So
yes,
this
sir.
also is another way to understand that these mirrors are not doing anything. Okay, if you remove this BS2, these mirrors are not doing anything. Okay, so Abhijit, it's good. So your question has actually clarified something, right?
Yes, sir.
Yeah. Okay.
Sir.
Now, yeah.
Sir, will there not be any interference, sir?
When there is no BS1? When there is no BS2?
Yes, sir.
There is no interference. Because, see, where is the interference? One photon is coming, and then it is coming to either D2. Suppose if, so what happens in this case? Transmitted will go to D1. sorry, transmitted will go to D2 and reflected will go to D1. In this case, in the case when you remove this BS2, so let's say it is transmitted. So the transmitted will come to D2 and reflected will go to D1 if BS2 is not there. So there is no interference.
So if you consider it as a wave,
Consider it as
wave.
Sir,
okay.
I have a doubt.
Yeah.
So you told that every so the source release one photon at each time. Then how? What is the criteria to select one photon is transmitted, one photon is reflected? How we decide it?
See, what is the role of a beam splitter? It will transmit or reflect the photon with equal probability, right?
Yes, sir.
So a given photon can be transmitted or reflected. It has both probabilities, right? Okay, have I understood your question?
Yes, sir.
So what is your question? One photon is coming.
Yes, sir.
So we don't know whether that photon will be transmitted or reflected beforehand. But we know that one of them only will happen, right? And if it is, if BS2 is removed, if it is transmitted, it will reach D2. If it is reflected, it will reach D1. And therefore, the population at D1 and D2 is n by 2, n by 2. This is our logic, and that is what I mean, if you do an experiment, that is what you will get.
Yes, sir.
Okay. Now, let us look at another experiment. That is, let's have a beam splitter here, and then let us take a source 1 here, which will send photons, and source 2 here, which will send photons. So photons are sent from here, or photons are sent from here. Then let's have a detector D1 here and detector D2 here. What is this arrangement? This arrangement is like remove first beam splitter, remove BS1. Okay. So if you remove, if you remove BS1, then you will not get this situation. So this is not exactly like removing BS1, but let's have this as another arrangement. So let's say I have a photon coming from here, a photon coming from here. But now we also say that these photons are such that there is only one, either a photon from S1 or a photon from S2 will come. Both will not come at the same time, because in all situations, I want to have only one photon at a time. Okay. Suppose a photon from S1 will come. Either it will come to D1 or it will come to D2. Correct? Let's say some, I will send n by 2 photons from here and an n by 2 photons from here. Then what will I get at D1 and D2 on an average?
So n by 2, n by 2.
I will get n by 2, n by 2. Because n by 4 from this, n by 4 from this, and n by 4 from this here, and n by 4 from this here. So I get n by 2, n by 2. Correct? And this is correct. Okay. Now what happens in this particular case? Okay. So what happens in this particular case? Okay. So that is very important. So what happens in this particular case is that in this particular case, your D1 and D2 Okay, I think you have given this answer, but I think it is slightly different. All the n will come here and nothing comes here. This is the result. For this experimental arrangement, this is the result. Okay, so now you may say that this is interference, and you may say that photon is interfering with itself. Then photon has a wave nature. Now this wave nature, or what? Suppose if you say we have understood interference happens only in the wave nature, right? Constructive interference, destructive interference, all these things we only know if there is a wave nature. Now this looks like interference. If you want to understand this interference, you have to say that photon behaves like a wave, or it has a character of a wave, which is manifesting in this experiment. Now, if you remove this BS2, it is manifesting its particle nature. If you keep this BS2, it is manifesting its wave nature. How do we understand this? Or what is the way to understand this?
Sir, I have a question, sir. Like,
Yeah.
if we take single particle, like, is it will be in a wave? Like, how can it will be in interfere, sir? Like, if we take double slit experiment, like it will strike at, if you have a screen, it will strike at one position.
Correct.
Then it's like a one particle, but if we tell that it's a interference of like, is it possible that interference of itself, like?
See, whether the particle is interfering with itself or not, what I want you to understand here is this particular arrangement. Okay, so let me draw that again here, because this is very important. So I have a source and I have these photons. I have a beam splitter. Now what happens to photon as this beam splitter? It randomly either will be transmitted or reflected. There is no doubt about that, right? So it will be either T or R randomly. This is very important. So whether it will be transmitted or reflected, we will not be able to say. No prediction is possible at BS1. Now you keep a mirror here. And now you keep a mirror here. And this is coming like this. This is coming like this. Now put a BS2 here. D1 here. D2 here. Now if you follow the transmitted photon, what happens to this transmitted photon at BS2 is random. It can be reflected or transmitted. That is this arrangement that I am talking about. And if you follow this reflected photon, same thing is true from this experiment. But when you consider this whole setup, even without doing experiment, you can predict that a photon that is coming from S will come to D. So all the n photon will come here, no photons will come here. That means what? This is deterministic. I can predict. I make this arrangement and I can predict that this is what is going to be a situation. And how nice it is that you have something to predict in quantum mechanics. And this prediction is possible. Okay, whatever is the reason why this, you may call it wave nature, you may call it interference, whatever it is. But what is very interesting is that I'm able to predict. Okay, without any error, all the photons are going to D1 is a big thing, isn't it? And we should celebrate this, because something useful can be done. Now we say that quantum mechanics, we can't say anything. It's not like that. So this is something which we can predict, that from S it will go to D1. And experiments show you this. Every photon comes from S will go to D1.
Sir, from intuition, what we can say, sir? Like, what, what is? I'm not getting like why it will go to N1. Sorry, D1.
Huh. Okay. So there are two issues here. One is this is what nature is. Okay. So nature is like this. Okay. Or in some sense, if you want to call, this is the nature. And second thing is how to get this. We have nature is like this means what? Experiment shows this. Now, how to get this result from theory? Okay, so this is a question. And quantum mechanics does it. Quantum mechanics, you can calculate this theoretically. This result quantum mechanics gives you. And third is how to understand. How to understand the mechanism of this phenomena. Okay, so this is one level. And fourth, how to use, how to put this to use. That is in applications. Okay, so we have made some observation and we have observed something. There is a determinism that is born out of quantum mechanics. Now this is an observation, so that is how the nature is. Nature is like this. Experiment gives you this result. So this is something which we have observed. Now, how to get this result from theory? And for that, we have to learn quantum mechanics. From the theory or from the postulates of quantum mechanics, you will be able to explain this is what should happen in this particular case. So if you want to do theory, you have to learn quantum mechanics. Now, how to understand the mechanism of this phenomena? That means what is happening to the photon, how a single photon is interfering with itself, what is happening to the photon at BS1, at BS2, in between BS and BS2, and how is it coming to D1? These are the questions which are related to how to understand this mechanism of this phenomena. Now, how to put this to use? This is applications. Now, I should tell you that we are doing extremely well. Experiments are good. Now we are able to do experiments. We are able to do theory very well because we have quantum mechanics at hand, and quantum mechanics, you can calculate using quantum mechanics exactly what is observed experimentally. Now, this is something which we don't have much of a progress. How to understand the mechanism of this phenomena, we don't have much of a progress. So this is something which is incomplete. Even now, we don't seem to understand how to, I mean, if I have to go to a school student and then I want to tell this, so there should be some amount of what is called some amount of maturity to not to ask troubling questions is required to deal with this. Okay, but if you are a child, you ask all kinds of troubling questions, and there is not much of comfortable answers to those uncomfortable questions. Now, over the last 20-30 years, there is a large understanding on how to use this for applications. For example, this phenomena can be used to something called quantum key distribution, QKD. You can use this in quantum key distribution, and quantum key distribution is very important in something called quantum cryptography. That means you want to make some secret communication. For that, you have to have cryptography. Okay, so this is very current and very hot topic, and a simple understanding of this phenomena can actually be put to use in sharing a quantum key between two distant observables, by which you can actually share secret messages. Okay, so this is a thing. So any phenomena that we study or we observe in nature, we will have to go through all these 4 steps. Okay, and ultimately, when you learn to use this in applications, you will convert your conceptual understanding into technology, and that will further improve the quality of life and quality of life for people and societies and things like that.
Sir?
Okay, so these are the steps. Yes.
So can we think of it like this? The probabilities are getting interfered, like the interference of probabilities. Like randomness is cancelling each other through destructive interference, and randomness is like adding to each other through constructive interference.
Yeah. So that's not the right way to understand, because probabilities are essentially all positive, so they don't cancel themselves, right? So probabilities do not interfere anytime.
Okay, sir.
Okay.
Sir.
Yeah.
I mean, here, sir, suppose a photon is received at D1, we can't say whether it is first reflected, then transmitted, or first transmitted, then reflected. That we cannot say. That information, information is not, we are not having. So.
Correct. So that is good. So the point you made is very nice. So a photon reaching at D1. Okay, so a photon reaching at D1, we cannot say is an RT photon or TR photon. That's correct. Yes.
So can we say that if a photon is transmitted, it will not get transmitted again, or reflected and it will not get reflected again?
We cannot say that, because that experiment number 2 that we discussed earlier tells you that that's not the case, right? Otherwise, we would not have got n by 4, n by 4, n by 4. If your hypothesis is correct, in this experiment number 2 that we discussed here, you would have got transmitted will always be transmitted. That means you would have got n by 2 here. And reflected will always reflected, means you would have got n by 2 here, right? But that's not correct. What we get is n by 4, n by 4, n by 4, n by 4.
Sir?
Yeah.
Sir, you mentioned that the probabilities can't be negative. So like one positive thing and one positive number, negative number cancel each other, but it cannot happen with probabilities. But if we think that odds in favor and odds against, so they can nullify, no, sir?
What odd?
Odds in favor of transmission and odds against transmission.
I don't understand that. What is that? Odds in favor?
Odds in favor, likelihood of transmission and likelihood against transmission.
So if it is against transmission, then that has to be reflection only. There is nothing else, right? There are only two possibilities here.
Yes, yes, yes.
So it is like saying either transmission or reflection, right?
Yes, so likelihood for and likelihood against, they might cancel each other. No, sir.
No, both are positive again, right?
Okay, okay. Okay, sir.
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 Sir,
Yes,
but
yeah. Yeah, please.
Sir, but at D2, we don't get any photons, which is where there is only a possibility of transmit and transmission and reflection and reflection, right, sir?
Correct. Okay, so from this you are trying to say, okay, now let me, since no photon comes to D2, TT and RR cannot happen. This is your conclusion, right?
Yes, sir.
Okay, so T at BS1 implies R at BS2 and R at BS1 implies T at BS2. Okay, now this conclusion, I mean, from this observation, this conclusion seems to be correct. Okay, this conclusion seems to be correct, but we don't know why.
Sir, if we take this conclusion is right, then above experiment will fail, right? The second experiment.
That, yeah. What I'm saying is, in this particular, there is a difference between second and this experiment, because second and this experiment are different in the sense transmitted photon is reaching BS2. Here, reflected photon and transmitted photon are both coming to BS1. Sorry, BS2.
But if you take a single photon experiment in the both the case,
correct,
then
correct. There is no difference.
Yeah, there is no difference.
Yes. So,
sir,
trying to understand that the second experiment and this experiment is what causing trouble, right? Yes.
Yes,
somebody.
how to reconcile this out, the results of the two experiments?
Yeah.
That is troubling.
Yeah. So there's some question somebody is trying.
Sir, suppose if we have a beam splitter in Michelson arrangement, Michelson interferometer arrangement, can you explain the beam splitter things? What will happen?
Michelson is also something like this only, no? What is the difference between this and Michelson?
Sir, some of the photons get reflected again and again.
So one beam splitter for Michelson interferometer.
Okay. So let me just maybe make some modification to this experiment. So what was the experiment number that I have here? Third, is it? Okay, that was third experiment. So let us have this fourth experiment. So let's say I have a source and then fifth, huh?
Yes, sir.
Okay, fifth experiment. The number doesn't matter actually, but just to keep track of so I have a beam splitter here call it as BS1, and then I put a mirror here, call it M1, and then I put a mirror here, call it M2, put a mirror here, call it M3, put a mirror here, call this M4, and put a mirror here, call this M5, mirror here, call it M6, and put a beam splitter 2 here, D1 and D2. Now what have I done with this mirror M1, M2, M3, M4?
So they are just
Increase the path length. Sir.
Yes, I have increased the path length. Okay, so path length in T transmitted arm is longer. Now, what do you expect at D1 and D2? If there are n photons, what do you expect? Now, if you believe that there was an interference before and the path lengths are same, if there was an interference, what will happen to the interference now?
So there will be disparity in the number of photons, but not 0 and n. Like,
There will not be, so no prediction is possible.
yes,
Can we say that?
yes, sir.
No prediction is possible. Okay, so let us say that, so if you say that this path difference okay, so if you say path difference is some d, okay, now when d is equal to 0, when d is equal to 0, that means there is no path difference, all the n come here and 0 comes here. Now for any d, there will be photons coming to both of them. Now you can find some particular value of d, call it as L, where all the n will go here and 0 comes here. And this is what happens in interference, right? So this behavior is exactly like what happens in interference. If you can tune your path difference in such a way that n0 can be made 0n, and then you increase L further for some particular value 2L or something, it will again be n0. So this is actually a more confidence it is giving that what is happening is like interference, because path length is what changes these populations. Okay, so this is another indication that what seems to be happening is an interference or something like an interference. You want to understand what this interference is due to, how single photon is interfering with itself. What does that mean? And things like that. So these questions, however uncomfortable they are, they come into this category of third category that I have shown here. So here I have listed this category. So these uncomfortable questions that I am asking come under this category.
Sir,
Yes.
sir, in this case, if instead of D1 we had a mirror,
Instead of D1.
yeah, like we just have one detector instead. I mean, the third case.
In the third case. Which is third. This is this one, right? Okay.
So instead of D1, if we had a mirror, so like if we think of the number of photons, then D2 should be n.
No. So where are you going to put this mirror here?
Yeah, like instead of D1.
Instead of D1, where a mirror like this?
Yeah.
Then all will be reflected back, no? All will be reflected back. Some of them will go up and some of them will come, some of them will go this side. Because beam splitter is only going to either transmit or reflect, right?
Oh, okay, sir.
So, yeah, so what you are saying is that if you have a beam splitter here and then a mirror here, so all of them will come and then come back. Then some of them will go up and some of them will go like this. That's what happens. Nothing will come to D2.
Okay, sir. Okay.
But why do you think of this configuration? Any
No,
reason?
sir. I was thinking if from beam splitter 2, if there was a reason to come to D2, and then there will be a contradiction.
Yeah, suppose one way of coming to D2, all of them coming to D2 is instead of putting a source here, okay, instead of putting a source here, you put a source here. Okay. If you put a source here on the top, instead of horizontal, you put it vertically. Then what happens? It is reflected here. Reflected will be transmitted. Of course, in that case also only TR and RT will come. But TR and RT will be at D2, not at D1.
Sir?
Yeah.
If we put the mirror at D2 instead of D1, then...
Anyway, nothing is coming to D2, right? If something is coming to D2 only, it will be reflected.
Yes, sir. Okay, sir. Good.
Yeah.
So can we just predict this, like nothing will, like if we put a mirror at D2, then like will it change the outcome? Because the outcomes are so counterintuitive that we cannot argue from the first principles here. Hello?
Yeah. So one point is that, okay, suppose you want to do an experiment by making all these configurations changed, you can do, but then we will be able to argue from basic principles of how a mirror works and how a beam splitter works, right?
But sir, for that interferometer case, like we cannot, for a single photon, we cannot explain like intuitively.
Yeah,
We don't have
but
any
that is our problem with intuition. Okay, so we don't have enough intuition. That's what it means, right?
So we still lack the intuition to explain other things.
Correct. So that is our problem. But that's not the problem of quantum mechanics. So why I am making a little bit of taking a little time on this aspect is that it's not that this is a very useful exercise, because what I want you to understand is that what you can do with respect to learning or doing quantum mechanics is you have so many experiments which are counterintuitive and you don't have an intuitive way of understanding them. But all of them can be calculated or explained using quantum mechanics. Okay, that is the power of quantum mechanics. So you have to learn this. Learning quantum mechanics is just learning this aspect. That's all. Even the experts who publish papers left and right in quantum mechanics also will not be able to give you convincing explanation to this question. And some of them may not be interested in the applications. But what is it that you have to learn is how to get this result from theory. Okay, so this is the business. Okay, so this is the business. And it is worth learning this business, because however counterintuitive your experiment is, quantum mechanics gives you the correct theory. And that is why this is so powerful and all encompassing. And it makes very important for every physics student to appreciate and learn how it works. Okay, so I want to make this point clear. In the process, if you are able to understand a little better than what you understood now about the mechanism and the phenomena and things like that, well and good. Otherwise, there is a lifetime to do this. But what you do in quantum mechanics in your master's course is that get the business initiated, learn the basics to do this business, to calculate things from the theory. Okay, so is that clear? So what is our business is to learn the theory. Okay, so that is what we will be interested in this set of lectures. So I wanted to motivate sufficiently with an example that tells you, by presenting a curious set of experiments, I want to tell you that what is possible with quantum mechanics and what is not possible, and what is the scope with respect to its applications and things like that. Okay, so I hope I have communicated the essence of what we will be doing with respect to this course. So I will stop here. If you have some questions, please ask.
Sir, you have mentioned that quantum mechanics is so powerful and all-encompassing that it can explain everything. The all-encompassing means it can explain everything. But like I have noticed that for helium atom, we cannot solve exactly using quantum mechanics. We cannot solve the helium atom problem exactly. So is that the inability of on our part, or like is it like a deficiency in quantum mechanics?
You see, helium atom you cannot solve exactly, but whatever you want, you can solve approximately, and you can solve to whatever approximation that is required. See, experiments and theory. So when I say all-encompassing, I mean that every experiment that you have, I mean, that has been done so far has been explained by quantum mechanics. So helium atom, you suppose you find out the ionization energy of helium atom, you can calculate from quantum mechanics. So like that, whatever experiment that you can do, there are methods to calculate. It may be approximate, but that approximation is enough to explain the results of the experiment.
Yes, sir. But like, is that inability is something our inability, or like is it a deficiency in quantum mechanics?
That's a theoretical limitation only.
Okay, like our mathematical tools are not efficient enough, or like advanced enough.
Correct.
Okay, okay. Sir. Answer just one curious like question. Like I don't know about quantum cryptography, but like QKD, is it like a quantum version of like public key distribution?
No, QKD is just a key distributed between two people. That's all. Two parties.
It's like in a classical encryption, we use the Fermat's little theorem. Like,
Yeah.
So is it a quantum version of that?
No, this is just between two parties, but it can be generalized to many parties also. Okay. Shivaraman, you have raised your hand. You have any question?
Yes, sir. Sir, on the third exam, please move up, sir. Third experiment.
Third, this thing, that is same as what is there on the.
Sir, you just said that the probabilities n/4 and 3n/4. How is it possible, sir?
No, I did not say that. That was one of the options that some of your friends said. So I listed all the options that all of you said. And then I said that finally I said what is going to be the result. Result is all the n photons come to D1 and no photon goes to D2.
Sir, there is also another probability that D1 gets all photons and D2 gets no photons.
That's the result. That is the correct result.
Okay, sir. Therefore, there are three possibilities. Yes, sir.
No. Those three possibilities are what people have guessed. Among them, there is only one thing that is correct. And the correct thing is n and 0. That's all.
Sir, how is n and 0, sir? Sir, there is also equal possibility that D1 get n/2 and D2 get n/2. Sir.
Yeah, that is what we intuitively think, but that is not what is happening. Okay, that is where I am saying that our intuition is not helping us here.
Yes. Okay, sir.
Yeah. Okay, so if there are no questions, then we can.
Sir?
Yeah.
Sir, here you want to emphasize means like why on D1 it is n or D2 it is 0, no, but you want to emphasize in which case the result will be n/2 n/2 and in what case it will be 0n or n0, right? That means how to understand this two distinct.
Correct.
Right.
Yeah.
Okay. Sir, this n and 0, that one can understand if we say this beam splitter introduce a phase of π/2.
Yes.
But that is not important, no, sir. Means you want to convey why it is n0 in which this case and why not it is n0 in the previous case, right?
Yeah. So what I am trying to say is that these observations are solid, right? We cannot change them.
Yes, sir. Yes, sir.
Okay. So from that observations, what conclusions can be drawn? That is what I have been attempting. No, in the last two classes also, I have been only attempting that. I am presenting an experiment and then listing the observations, and from that, what can we conclude? What can we learn about it? It is like saying that let us say you don't know anything and you are just looking at the nature, and nature is presenting you the clues.
Yes, sir.
Okay, from the clue you are trying to build up a story.
Yes, sir.
Okay, so that is what I am trying to do. So in this experiment, nature is giving me this clue. From there, I know that this is random. From there, I know that this should be the probability. From there, I know that probability cannot be used to construct the state. Okay, like that I am building up one by one. And from the beam splitter, I know that it is not selecting one of them. Okay, and when you put this, from all that randomness that we are talking about, there is a determinism that is emerging.
Yes, sir.
And this determinism can be made use of.
Yes, sir.
Right.
Sir, then this theory, what we say, this is phenomenological only. means we construct based upon the experimental observations, right? Yeah.
If I construct a theory based on these experiments,
Yes,
it is phenomenological theory.
yes, sir.
But if I construct this theory, and if
Yes,
this
sir.
theory is sufficiently general that it can work in every other situation,
Yes, sir.
then I can claim that, okay, I started with a phenomenological theory, but
Yes, sir.
every theory will start like that only, right? You have to have a
Yes, sir.
contingency with the nature.
Yes,
So
sir.
every theory will start that, but if you can make it general enough that
Yes,
it can
sir.
work in every other experiment, then it becomes a fundamental theory.
Oh, that way. Okay, sir. Thank you, sir.
Sir.
Yeah.
So like whatever I have understood, that apparatus like can be thought of as either a unitary operator or like a Hermitian operator, like either a unitary operator or like an observable. But but what about depolarizer, sir? Polarizer can be thought of as an observable, but depolarizer it actually increases the randomness. It makes a polarized light into unpolarized light.
Yes. So essentially, if you say that there is a depolarizer, we cannot talk of depolarizer in the context of quantum mechanics that we are discussing now, because a depolarizer is not only it is actually changing the quantum state in such a way that it becomes from a pure state to what is called a mixed state.
Yes, yes.
Okay, so that is something which is a little different from. So whatever we are going to talk is only saying that the polarization is not disturbed, but the polarization state is changed.
But like this depolarization is increasing the entropy. You can think like
Correct.
that.
So when entropy comes into picture, then we have randomness at different level.
Okay, but how can we like reconcile entropy with quantum mechanics? Because quantum mechanics we usually study without entropy, consider entropy.
Yeah, that is the conflict that I am trying to point out. Quantum mechanics we study without any reference to entropy, as long as you study quantum systems as closed systems. But when you say you have a depolarizer, it cannot be studied as a closed system.
Okay, sir.
Yes. We don't study that in MSc at all, in MSc quantum mechanics at least. You may study a little bit when you do a quantum statistical mechanics, but quantum statistical mechanics system is not isolated, a closed system, because it is in contact with a heat bath and there's an open system.
Yes, yes.
Sir?
Yeah.
In the third experiment, if we change, means how we place the mirror, will it affect the result? Like if we don't place the mirror as 45 degree, we change the angle, then the photon path will change. So in that case also path length will change, and the population at different detectors should change, no?
Yes. If you change the path length, the population at different detectors will
So
change. But one
that
thing
can
that
be,
you have to remember is that you should make them incident on the second beam splitter.
yeah.
Okay, so then if you
So
change
the
the path
angle
length,
will also affect the population. Means how we place the mirror.
yes, if you whatever is the mechanism through which you change the path length,
It will affect the
it will
population.
affect the population.
Okay, sir. Thank you.
Sir, like some entropies, kind of entropies are always increases for an isolated system, and some entropies are bounded. So how can we like call both of them entropies?
Which are entropies that are bounded?
Like von Neumann entropy.
See, if you take if you take von Neumann entropy also for a system, a general system, okay, so if you take a two-level system or something, then von Neumann entropy is bounded. But if you take a general system, it is also, and entropy always increases is a statement for a thermodynamic system, right, which is infinite system. So if you take an infinite system and then look at one entropy, that also will not be finite.
Okay, sir. But like, are they like same kind of entropy, or like are they fundamentally different?
There is some difference, but with respect to with respect to a measure of randomness, they are same.
Okay, sir. Thank you, sir.
Okay, so then we can close.
Thank you, sir. It was a good way to
Sir.
start the introduction to quantum mechanics.
Oh, thank you. Thank you.
Sir.
Hope you all enjoyed. Yes, Satish.
Yes, sir.
Definitely, sir.
So in third experiment, can we say that at D1 there is constructive interference, and at D2 there is destructive interference?
Yes, you can say that.
Okay.
If you can understand, I mean, this is one way to say, no? So it's just a language. Okay, whatever pleases you, you can say. Okay, if this pleases you, you can say that. There is nothing wrong with that.
We don't know what happens there. So
yeah, so you ask, see, the question like this is there, no? So you say that it's a constructive and destructive. What is interfering with what? There is only one photon. Which is constructively interfering with what? Okay, so that question is there, right? So that question, we have to have some way of answering that question.
Sir, that is same as single slit single photon experiment, right? Like
that's same as single photon.
like, yeah.
So photon acts as a wave here, sir.
Like that's another way to please yourself. Yes.
Sir, what I'm saying is, like in double slit experiment also, you will see the interference pattern after n number of photons coming out of this one.
Correct.
But it is single photon experiment. Like if you take single photon experiment, like one after the other, you will see a pattern of interference, right?
Correct.
Yeah, I think it's similar to that. Also, we could not answer with the particle nature.
Correct.
Yeah, maybe
yeah,
it's
so that's
similar to this.
Yeah, so it is useful to compare double slit experiment with this. So maybe I request all of you to read double slit experiment and then try to see how can we understand these two things together. Actually, there is no difference. Quantum mechanically, both are same.
So like I have understood that in for polarizers we have coherence, and like for beam splitter as well, like we have coherence, and for depolarizer we have decoherence.
Correct.
That's the way to understand.
Yeah. Shitikanta, you have something to say?
Yes, sir. Sir, I am saying, let us say, sir, we send just one photon today, and after 1 year we send another photon. Sir, both will come to D1.
Yeah.
So this, even though I convince sir, I have this doubt. Means at source level itself, photon knows that there is another beam splitter, so it decides its path before getting emitted from the source. That part.
Yeah. That's. I mean, that's somewhat. Your discomfort is not.
Yes, sir.
Not only yours.
Yes,
okay,
sir.
so this discomfort is there for all of us. So there is someone called John Wheeler who actually tried to do. I think that first beam splitter. Whether the photon knows before coming to first beam splitter that there is another beam splitter.
Yes, sir.
Or so where actually this decision to go to D1 and not to go to D2 is taken.
Exactly. Yes, sir.
So that question was there. So what Wheeler thought was, okay, I will decide whether to put the second beam splitter or first or not only after the photon crosses the first beam splitter.
Yes, sir.
So suppose if the photon is crossing the first beam splitter,
Yes, sir.
Then suddenly he will remove the second beam splitter.
Yes, sir.
Then what happens?
Yes, sir.
Or you don't put the second beam splitter. After the photon crosses the first beam splitter, you put the second beam splitter. Then what happens?
Yes,
So
sir.
this is called Wheeler's delayed choice experiments.
Yes, sir.
Okay, so this was very famous. So maybe you can do a little bit of reading on that, or
Yes, sir.
sometime we can discuss
Yes, sir.
these experiments also. But there are so many experiments, very interesting experiments in quantum mechanics.
Yes, sir.
And I think over the last 20-30 years, so many experiments have been done, which have helped us to understand nature in a much better fashion than in the olden days. People used to do only thought experiments, but now
Yes,
technology is so good that you can actually do real experiments in the laboratory.
Yes, sir. And sir, all these all these theoretical prediction falls in line with this experiment.
Yes,
Also.
yes, with no exception.
No exception.
That is the power of theory, like
Yes,
quantum
sir.
mechanics.
Yes, sir.
Whether you understand or not, you can calculate.
Yes, sir.
Calculations are impeccable. Accuracy you will get.
Yes, sir.
So I hope you are all motivated now to learn quantum mechanics and understand how important a theory it is.
Yes, sir. Very much, sir.
Yeah.
Yes, sir. Definitely.
Okay, so let me see what best I can do to teach you the tricks of the trade, which are very important. And after we learn some basics, we will come back to this experiment 3 and then calculate and show that all the photons will come to D1.
Sure, sir.
Okay, so then we can close.
Professor, shall we close?
Yeah.
Because I am seeing the excitation, therefore
yeah. I mean, this is expected because quantum mechanics is like that, which is always. I mean, and also I try to follow this route, not a conventional route, to introduce quantum mechanics, so that some people will be at least sleepless for 1 or 2 days.
So,
yeah, so we can.
Shall we close?
Yeah.
Yeah. Okay. Thank you, Professor.
Good night,
students.
sir.
Good night.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.